Okay, so Harish, over to you. You can proceed with the hands-on session.
Yes, ma'am. Okay. So either you can follow along the video or I will simultaneously do here. So if you have any doubts, you can stop me and ask. Okay. First, I will start from downloading itself so that you have a clarity on how to extract everything. So first I'm
Hello,
going to,
Harish.
yes.
Will there be any difference between using WSL and Ubuntu?
No, actually, there is a slight difference that only the in the terminal. So if you are using WSL, you will first initialize with the command WSL and then use it or open a Ubuntu terminal. But if you are on a Ubuntu machine directly, then you can just open it. But there will be one small change when you download and copy paste, which I will demonstrate right now. So the main thing is when you are creating a folder inside your case directory. After you download the zip file, extract it and place it in a convenient way such that all the command works. So you have to navigate through your command prompt and go to the case directory and then follow along. So that is the only change which you will be having to face. So otherwise it will be fine.
Sure. During the tutorial, can you please mention wherever we have to be careful?
Yeah, sure. So I'll start from downloading. Okay, after you download, this is the most careful part which you have to be. While extracting, you have to use either WinRAR, a file like WinRAR, and use extract here, or you can use the Windows default of extract all. So once you do this, you will have a case file which looks something like this. So when you double click on this, it will have these two folders. So you have to make sure that you are copying this folder and not this folder. For example, you will when you extract it, you will have something like this. Okay, you will have something called the moving airfoil. When you double click on it, it will have another folder called moving airfoil. So this is what you have to copy when I actually tell you to do. So I hope this is clear, because only if you get this right, every other command will work. So now I will open the drive link which I have shared and open the PPT so that we can follow along. So the first thing is we download the case files and I'm going to open a command prompt. So either you can just search for Ubuntu and open the terminal, or you can open a command prompt. So I'm opening a command prompt and then I will type WSL, give enter. I will enter into the Ubuntu terminal. So this is the main change which you will be facing if you are on a Ubuntu machine directly. Instead of doing all of these steps, you will directly open a terminal. And then if you are having multiple OpenFOAMs on your machine, you have to specify the alias. In my case, I am loading OpenFOAM 9 with the alias which I have mentioned. But if you do not have other versions, if you have only OpenFOAM 9, you can skip this step and follow from here. Okay. Now, first we will navigate to the working directory, which is using the command cd foam run.
Harish, can you please repeat your last line? What did you say?
Okay, if you are
After
having
WSL?
if you are having multiple OpenFOAM versions, you have to specify the alias. So if you have multiple OpenFOAM versions, you will have to do this. But if you installed only OpenFOAM 9 for this workshop, maybe you will not have multiple OpenFOAMs, then you can skip this step. But if you have multiple, then you have to specify the alias and load OpenFOAM 9 specifically so that this simulation will run. If you don't have, you can skip this step and start from the cd foam run. Okay, the next command would be to create a directory, which I will be doing using the command make directory airfoil case. So I have created the airfoil case, which we can see from here. I have a folder called airfoil case. Now I will enter into the folder by typing the command airfoil case. Okay, now we are inside this directory. You have to make sure that you are inside this directory specifically. Here you will have your username. Then what we have to do is open an explorer and paste the file which we downloaded initially, this moving airfoil. So this folder will have two folders called KOmega-SST and Spallet Almaraz. So you have to exactly copy this folder, moving airfoil, and paste it in this directory. So this one. Okay. Is it hiding this one? Okay, I hope it is clear now. Okay, once you have pasted this in this directory, you have to go
Is it for everyone, or actually in the PPT it is telling that it is only for who are using WSL?
No,
we are using directly Ubuntu. It's coming that explorer.exe command not found.
yes, you instead of using explorer.exe, you will directly open the file location, which is this location. Inside the run directory, there you are creating a new folder called Airfoil case. Once you enter this, you have to paste the file which you downloaded. So that is the only difference.
Yeah, okay.
After this, it will all be same. There is no difference. Okay. Now we will see what is the next thing which we have to do. We have to enter the case directory using this command. So I will do cd moving airfoil. Now, if we see, we have two turbulence models, as Professor explained. We are going to do two turbulence model, namely KOmega-SST and Spallet Almaraz. So each of them has two more folders inside. The KOmega-SST has case files for two separate Reynolds numbers, and again Spallet Almaraz has Reynolds number of two different things. So for demonstration purpose, in the PPT, you will find only the tutorial for KOmega-SST for specifically RE1E6. But if you want to follow any other things, you just have to enter the folder accordingly and you can follow along. But again, to keep up with the PPT, I'm going to do KOmega-SST at RE1E6. But if you just want to enter Spallet Almaraz inside RE1E6 or RE20E3, you can do so using the cd command. It is up to you, but for tutorial case, I'll be doing KOmega-SST, and inside that, I'll be choosing RE1E6. So once we are inside this directory, everything else from the PPT should work, regardless of it is WSL or Ubuntu machine. Okay. The next thing which we have to do is copy the 0.original file to 0. So you can find this using your Explorer as well. We are having, if you are finding zone.identifier files, you can safely delete it. It is not a problem. You will get this issue if you are using a Windows extract all feature. But if you are using something like WinRAR, you will not ideally get this problem. So choose accordingly, and you can safely delete the zone identifier files. It is not a problem at all. Okay, once you go inside, you will find something like this. So we will have 0.original, constant, system, and there will be two files called allrun and allclean. We will look at that later. And you will also have para.foam to open the paraview file. If you already have paraview installed, you can double click this to view the results after you run the simulation. But if you are typing parafoam, it is mostly not going to work because this has a lot of colors, and parafoam doesn't allow that. So it is better to install paraview and follow along. So we will shift to the PPT and follow the commands. The next thing which we have to do is copy the 0.original file to 0.
Okay.
After you copy the command, you will find all the files like 0.original, all clean, all run, and everything. Now again we can do the block mesh. So first we will look at what is there inside the block mesh. Either you can open it through your terminal itself, like notepad.exe space system/blockmeshdict. Either you can do that, but if you are working on a Windows machine, then you can enter into the system folder and open the block mesh dict using Notepad or Visual Studio Code or Notepad++ as you wish. I'm personally preferring VS Code, so I'm opening using that. If you open the block mesh dict, you will find more codes like this. It is okay if you don't understand any of these right now because you're not exposed to advanced block mesh yet, but you will find something like this naka0012.obj. So this is the object file, which is a wavefront geometry which we have downloaded from existing geometries, and we are using that geometry to mesh it. I think during the tutorial someone raised a question if we can download a CAD model and then mesh it using block mesh. So this is one such case where we are using block mesh to mesh an existing object. So we have kept that specific object in the location of constant geometry. So this is the standard structure OpenFOAM understands. So here we have placed the object file, and we have all the other files under system for controlling. So we have viewed the block mesh dict. It is okay if you don't understand any of these right now, you will learn it later. But the next main thing is extrude mesh. As professor explained, OpenFOAM cannot actually do a 2D case. So everything in OpenFOAM will be converted to 3D, and then we will define the boundary conditions of front and back as empty so that it behaves 2D when you post process. So this extrude mesh will take the 2D block mesh which is created and it will convert it into a 3D. So you can again explore the extrude mesh dict. So you need not worry about whatever the code is inside. The main objective here is to explore dynamic mesh dict. So we will do accordingly. Then we will see set of functions which we are going to use here. The first thing is force coefficients, which will automatically calculate the coefficient of drag, coefficient of lift, and coefficient of moment such forces. So there are set of parameters which you have to give as input, such as the patch. Here the airfoil is the name of the patch, name of the body on which we will be calculating the forces. So we have defined that, and we have the free stream density, the lift direction. Here it means X, Y, and Z direction. So the geometry is prepared in such a way that it is on XZ plane. So the lift is on Z direction, the drag is on X direction, and the center of rotation is at 0, 0, 0. So these are all defined based on the mesh we have prepared. So we will view the mesh before we run the simulation actually. So the pitch axis is through Y because the geometry is in XZ direction. And these are the just what we learned through the turbulence models. So the free stream velocity, which is mag u infinite, is 1. The length, reference length and area reference is estimated to be 1 here. Okay, that is all about force coefficients. We also calculate residuals like we do in commercial software like ANSYS, but we cannot view as we do, but we will see that finally. And we can also calculate Y+. You have the files, you can explore the library later. Okay, now we are going to see what is there in the constant folder. We already saw that we have the geometry in the geometry folder. Other than that, we have 3 files, namely the momentum transport properties, which is always there, and there is dynamic mesh dict. Okay, before that, is everyone following along? Does someone have any problem, right? If you have some problem, you can please turn on your mic and tell me before I proceed, because now we are going to see the dynamic mesh.
Hello.
Yes. Yeah.
What is the role of Y plus in meshing? Actually,
Okay.
Y plus ranges if less than 5, then
yes,
layer
actually,
is in
yes.
a sub layer, and if Y plus value is
I get it.
lies between 5 to 30,
The
that's
explanation is beyond
rough
the
estimate.
scope of this tutorial. So we cannot be explaining Y plus right now because we have to do turbulence models, 2 turbulence models, and sort out the bugs. So please, check out the documentation and see how Y plus influences the simulation. So that is beyond the scope of this simulation or tutorial. So kindly read through the documentation.
Thank you so
Is
much.
there any other doubts regarding the case setup as of now? Okay, if there is nothing, I'll just proceed along. The momentum transport file will actually talk about the type of turbulence model which we are using. So we are using RAS, which is Reynolds Averaged Navier-Stokes. And under RAS model, there are different models such as K epsilon, K omega SST, Spallet-Allmaras, but in this tutorial, we are going to use K omega SST. If you open the momentum transport file in the Spallet-Allmaras folder, in place of K omega SST, you will find Spallet-Allmaras here. That is the difference. This transport properties will give you the value of kinematic viscosity. So the way we set up this file for this tutorial is that we chose a velocity, we chose Reynolds number and a length scale. So the velocity chosen as 1 meters per second and chord length is 1 meter, and the Reynolds number chosen is two different Reynolds number. One is 1E6 and the other one is 20E3. So based on that, using this formula, we can calculate the kinematic viscosity, and instead of using a standard fluid with a standard kinematic viscosity, we are going to set the velocity and the characteristic length, and we are going to choose the kinematic viscosity. So I am changing the kinematic viscosity here, that is the new by symbol we are entering it. The value will be 1e minus 6. So either you can just type 1e minus 6 here, or you can type by decimals. It is up to you. OpenFOAM can understand both of them. And we are running a Newtonian simulation, so we have mentioned Newton. And this represents the dimension where this is m, l, t, which are the three major physical dimensions which we use to represent SI units. Okay, then the main file which is we are interested in for this tutorial is the dynamic mesh dict. So we will explore this. You could recall this setup from professor's explanation. First, we are calling the motion solver called as the dynamic motion solver FB mesh, meaning finite volume mesh. So we are calling this function so that it understands the rest of the codes which is present below. So the solver library, which is defined here, it is called as library FB motion solvers.so. So this is a standard way to call a function, call a solver. The motion solver which we will be using for this tutorial is interpolating solid body. There are many other motion solvers as well. You can check the documentation if you want to explore. And the solid body motion function which we'll be using is oscillating rotating motion. So this is the motion function which we will be using to oscillate the airfoil. As professor said, there are many ways to perform the dynamic meshing. You can give your own path or target lines, or you can use existing functions to define the oscillations. So in this case, we are using oscillating rotating motion. So again, the patch is called the airfoil. The center of gravity is present at 0.5 on the x-axis, 0, 0 on the z-axis. The inner distance and outer distance I will explain after we perform the mesh. So the oscillating rotating motion coefficients are the essential functions which this function will understand. So these are the parameters which we have to essentially give as input so that this function is properly called and it performs the simulation. So the main parameters are the origin. We have to define the origin of rotation. In this case, the mesh is made such a way that the origin is set at minus 0.25 on x-axis, 0, 0 on y and z-axis respectively. The amplitude is given as 0, 15, 0, which is xyz, but you can just give 15 alone and it will still take it. It does not require any specific direction, but since they have a syntax, we are using this. And omega is taken as 6.28. This is just a value of 2 pi. It is taken in the SI units of radians per second for omega, which is angular velocity. So this is all about dynamic meshing, which we will be performing right now. If you want to explore this, you please do not touch these parameters and origin as well, but you can alter the amplitude and omega to see much faster oscillation or slower oscillation. So that is all about dynamic meshing as well. Now, first we will make the mesh and we will see how the initial values for the turbulence are made. So if you have just followed along till here, please comment yes or something in the chat box. Or if you have doubts, you can tell me, because next we are going to proceed with making the mesh. Yes, the center of gravity is depending on the geometry which you are having. I will explain it while viewing the mesh. So the center of gravity is important. It is essential to declare it here so that the simulation is realistic by physics. So yeah, it is important. For specific geometry, it is fixed. If you are going to change the airfoil and if it is shifting by the coordinates in the 3D space, then the center of gravity will change. So I assume that nobody else has any doubts. So we will see how to perform the mesh. First, we will open the terminal and we will make sure that we are in this folder exactly. K omega SST RE186 to follow along here. But if you are using Spalat Almaraz or different RE, make sure that you are in some Reynolds number folder so that block mesh actually works. So when you type ls, you have to see all these files. So only then the block mesh command is going to work regardless of which turbulence model or Reynolds number you are using. So you just type ls and you must be able to see all these files. Now I will type block mesh. This will make the mesh. So make sure it ends without any errors or problems. Then immediately you just do the extrude mesh. So extrude mesh will take the 2D mesh which is prepared by the block mesh and make it into a 3D mesh. So again, this has to end without any errors. So now we will view the mesh first, then we will see how to run the simulation. So to view the mesh, you can just double click on para.foam file which is already there, or you can type parafoam if you are on an Ubuntu machine. But if you do not have a ParaView already, please install it, else you can't view the mesh properly. Okay, once you give apply on the left panel, you will see something like this. So we have to change the way we view. So you have to press the plus y normals here. It is on the top. Only if you press that, we will be seeing. Because our geometry is made in such a way that it is on the xz plane. So we have to view it on the y normal, through the y normal plane, positive y normal. So we are pressing this command. Now we are just seeing a surface, right? So to view the surface along with the mesh, you have to press here the surface and choose surface with edges. So once you choose surface with edges, you can see the mesh. Okay, this is a structured hexahedral mesh, which is suitable for running an airfoil case. And we can also do mesh morphing, which we are intending to do in this tutorial. It is not an overset case, just in case if you want to know, this is a mesh morphing case. So this is the airfoil body. Now we will see how we can view the boundaries here. On the left panel, you can see these things. By default, it will have the internal mesh selected. But if you just want to view the inlet, you can select only inlet and give apply. So this is the inlet patch in this case, and the outlet patch will be in this area. And as we were explaining how OpenFOAM takes only 3D and not 2D, you can see that there are two planes here, the front and the back. So these two are defined as empty so that the mesh actually behaves 2D, which we will explore further while we are exploring the boundary conditions. Now, the major thing which we are interested in is the body, the airfoil. So this is the airfoil which we will be working with. Okay, after you view all of these, if you want to reset, press on internal mesh, deselect everything else and press apply. Now you can press the y normal plane and get to the default view. So this is majorly the mesh. Now we will see what was the inner distance and outer distance which we were seeing in the dynamic mesh dict. So this is the file of dynamic mesh dict. Here you can see there are two parameters known as the inner distance and outer distance. So inner distance refers to the distance from the origin or any reference point if your body is not at the origin of the moving coordinate system attached to the body which undergoes motion. So to understand simply, you can see the value here is 0.01. The mesh here, the center is at approximately 0.01 where there is a deformation here. So you just imagine that mesh is rotating and it will have an anchor point here, which is inner distance, and for outer distance, which is defined as 4 here. So this will have an anchor point here. So whatever mesh morphing is happening, the mesh motion is happening, it will be because of the motion which is happening on this area from 0.01 till the 4. So you will understand this better when we actually run the simulation and see how the mesh morphs. So until now it is theoretical, and you just know this is the inner distance and this is the outer distance approximately. Okay, if you couldn't make the mesh, please tell me what problem you are facing. You can turn on your mic and tell me what the problem you are facing right now. Yes, I can see your annotation, but I couldn't hear anything. Okay, if you have any specific part that you couldn't understand because I was going fast, please tell me that, I will clarify again. Okay, so converting 2D mesh to 3D mesh is through a single command. Once we type the block mesh, so I have typed the block mesh here, it will create a 2D mesh, which is not something which OpenFOAM can solve. So we have to just type extrude mesh command so that the 2D automatically gets into a 3D mesh. Extrude mesh is a folder which is already defined. We will see that. So this is the extrude mesh dict. We are taking, this is a file which we are not actually interested, or we can't explain it right now. So what this file actually does is, it will take the 2D mesh prepared by block mesh and it extrudes into a 3D mesh which the OpenFOAM can use and solve. So that is all about the extrude mesh, and that is how we change the 2D mesh to 3D mesh. I hope it is clear now. So the mesh morphing, okay, after the extrude mesh, we did not do anything as of now. So once the mesh is done, we will start with the simulation. Now we have to learn what is parallel processing. In many cases, parallel processing will come in handy when the case is very large. So your system, the CPU which you are using, will have multiple cores, or known as the multiple CPUs. The central processing unit, the chip, will have multiple cores which can do computing works simultaneously. So we call that cores. So these cores will be different for different processors which we will be using. So in my case, I am using a processor which has 8 cores. But if you do not know how you can find the number of cores your processor has, you can follow these commands from the PPT, or you can just follow along what I am doing right now. So first, open your task manager. So after you open the task manager, on the left panel, you will be having something called performance tab. So press on the performance tab and press CPU and scroll down, and you will find the number of cores. So these are the number of parallel processes which you can run. So if you are intending to do a parallel processing, then you must remember this value, which you should be very careful of, else the simulation is going to throw error. So I will give you 2 minutes time. You just check the number of cores you are having if you want to do parallel processing. Else I will tell you what to do after we calculate the turbulence values. Okay, if you are on an Ubuntu machine, please check the chat box. Viraj has dropped a command which you can use to find the number of cores in your PC. Okay, now we will see how we are calculating the initial turbulence values, which is the K, omega in this case. But if you are using Spalet Almiras, there will be another file called new tilde. But first we will see how K and omega is calculated. So you can check the documentation. I have already shared the link of this. But if you just want to find, you can search for K omega, SST and OpenFOAM. Then you can press on the first link. So this is the value which professor was explaining. Here, the K is turbulence kinetic energy, which is calculated by this formula where I is taken as intensity. In this case, it is 0.05 or 5%. and the u reference, the free stream velocity in this case, is 1 meters per second. So when you plug in these two values, we will get the k value, which is 3.75 10 power minus 3. But how is this value useful? Where we are going to define it? So we are going to define these in the boundary files. So if you remember, 0 is for the boundary files. So when you go inside the 0 files, you will find all these 5 files. The u, which is velocity, the pressure, k, omega, and nu t. So based on what you have done previously for the icofoam, simple foam cases, you will have an idea on what is the pressure and the velocity file. But to run the k, which is a part of the turbulence model k omega st, once you open this file, you will find something like this. Here we will have a command called the internal field uniform 3.75 10 power minus 3. So this is the value which we just calculated using the formula. It is also mentioned here. So this value is what we are defining at the inlet for boundary condition and at the outlet as well. And for the wall, in this case airfoil, it is taken as KQR wall function. It is one type of boundary condition which we can use for K on a wall boundary. Okay, so this is the value of K which we have defined. Similarly, we also have the omega file. So inside the omega file, we will calculate it using this formula. So it is k power 0.5 divided by c mu power 0.25 L. So the c mu is a standard constant valuing 0.09. The k is the value which we just calculated, which is this value 3.75 10 power minus 3, and L is the reference length scale. In this case it is 1. So when we plug in all these three values, we will get the value of omega, which in this case is 0.11. You also have the formula here just in case if you want to calculate it on your own. And similarly, we are also defining it at the inlet, outlet, and on the wall as well. Okay, since the turbulence specific dissipation rate, which is omega, we are defining it at the airfoil, inlet, and outlet. When we put $internal field, it will call the value from here. So we are defining the value here, which is uniform 0.11, and we are calling this value here using the command $internal field. So whenever or wherever you mentioned $internal field, within that specific file, it will take the value from here. So if you change the value only here, all the values will be changed here as well automatically. You don't have to change it manually. So that is the purpose of doing this way. So the other boundary condition is the nu t. So nu t is turbulence viscosity. So it is a practice to just take it as 0 as initial value through wall, inlet, and outlet. So as I was saying, the front and back is always taken as empty. So regardless of what the boundary is, the front and back is given as type empty. And in the K as well, you can see the type is empty. In the omega as well, the front and back is kept as empty. So this means the front and back is defined as empty so that the mesh will behave as a 2D mesh. So if it is a wall, then it will be a 3D mesh. So this is all about the boundary conditions. Now we have to run the simulation. So I hope by now you already checked the number of processes which you have, so that I can explain how we can do the dynamic meshing. Okay, now I will tell how to edit the decomposed par file. So how you can find the decomposed par file is that the location of the file is under system. So under system, you will have this file called decomposed par dect. You open this. So here you will have a value of 8 by default when you download the case. But this is the number of processor which my computer has. But if your computer has only 4 cores or 6 cores, then you have to change the value accordingly here. And you also have to change the n. The n here depicts the number of subdomains you want in the x, y, and z direction respectively. So this is a geometry which is there in the xz plane. So we are discretizing the x direction by 4 and z direction by 2, but not discretizing anything in the y direction because it is just a 2D case anyways. So we are discretizing the x in 4 and in 2. But if you're just having less number of cores, what you have to do is you might have to follow this. so that it is suitable. So if you have 4 number of cores, you just change the n to this. Instead of 4, 1 and 2, you can change it to 2, 1 and 2. If it is 6, then you can change to 3, 1 and 2. If it is 8, you can just leave it with the 4, 1 and 2. So the rule of thumb is that when you multiply x, y and z, we have to get the number of values. So you can see in this case 2 times 1 times 2 will be 4. So similarly 2 times 1 times 2 will be 4 times 1 times 2 will be 8. So that is the rule of thumb you have to follow. Just in case if your processor has 12 cores, so what you have to do is 4, 1, 3 probably. So you have to make sure that you are discretizing properly. Now how to discretize actually? If you are going to run parallel processing, first you have to open your command prompt. So if you can see, again we are in the same directory. So I am typing ls, so we can make sure that we are in the right directory. Now here I am going to type decompose par. So once I press this or type this, you can see something like this. So all the number of cells which you have will be distributed in some way to all your number of processor. In my case, it is 8. So we are having 0 to 7. You can see processor 0 to processor 7, which is 8 processors. So it is splitting on its own. You don't have to do anything other than editing the decompose par file. So once you decomposed, you can start running the simulation. But till now, if you have any problem with decomposing, just please tell me.
Can you just show the last
which one?
how to solve?
Okay, the last command is decompose par with P capital.
Okay.
So after you run the decompose par, it will look something like this. So after this, we can start running our simulation directly. But if you are not running a parallel process, just in case, if you are not doing the decompose par, at this point, you can directly type pimple foam with F being capital and press enter, and your simulation will start right away. But it will take a lot of time since it is running on a single core. But since we are trying to do it in a multiple cores, you have to type this command, which is also there in the PPT. You can copy paste or you can follow along. So it is MPI run space -np. Then you have to specify the number of processes. So in my case, it is 8. So I'm typing 8, but if it is less or more, you have to carefully mention that. So we are what we are doing is we are calling multiprocessor, so which has a command mpi run, then -number of processors 8, then the solver, which is pimple foam in this case. So pimple foam space, then you have to type parallel. So it actually runs in parallel. So everything is just one line. You can also find the same in the PPT. So first we run the decompose par, then we are trying to run this command. So if you are having less number of cores, please make sure that you are changing this value. Okay, once we type this command in the command prompt, you can just hit enter and the simulation will start right away. It will take quite a while. Between that time, if you have any errors or any problems, any clarity, please turn on your mic and ask me before the simulation ends.
Hello. Yeah, hi, this is Yashwant. Okay. Actually,
Yes.
I am facing some problem regarding the simulation, right? I have done, I've done till extrude mesh. After the extrude mesh, if I'm opening the paraview, there's nothing to show over there. So will you please help me out?
Okay, have you installed ParaView already?
Yeah, I have installed all.
Okay, did you press the apply on the left button?
Apply?
There will be a green color button on the left named apply. So you have to press apply to view the mesh.
Wait. Opening paraview directly, right?
Yeah, you have to open ParaView directly. And after you press apply,
Then
you will get, then you have to press the Y normal.
Then we have to press
Y normal. Let me show you. after you open ParaView, this button apply here will be highlighted with green color. You have to press this. Then you will see something like a line sort of thing on the window. After you see that, you have to press this button on the top. So the plus Y. Yeah. So that will make your geometry in the XZ normal plane. Sorry, Y normal plane, which is XZ plane. So the geometry is made in XZ plane, but by default, the OpenFOAM loads in Z normal. So you have to change it by pressing this button. Then you can see the surface.
Then
after that, you change the surface to surface with edges to view it.
Hello. Okay. After Y plus, then what we have to select?
Yeah, that's it. Then you can view the mesh by selecting surface with edges over here. So this part will show as surface. Press that, you will get a drop down box.
No, there's nothing to show over there. There's nothing to show in the drop down menu.
Can you please drop the screenshot on the chat?
So can I share my screen?
I don't think that is permitted, but you can share the screenshot on the chat.
We are getting an error whenever we are running this parallel, like convergence criteria not found, no character convergence criteria found. And finally, it is getting that invoking MPI robot causes Open MPI to kill all MPI processes.
Then maybe you just selected the wrong number of processes. So that could be a reason.
No, actually, I changed the number of processes and we have 6 cores. I checked it.
Okay.
Actually, it is getting like no convergence criteria found. Pimple, no convergence criteria found. Actually, in the message, a lot of big message is there.
Okay,
no convergence. Yeah, I will drop.
Hello.
Ishwant, did you check? Have you placed a space between the small e?
Where? In that
column. Is there a space?
Good mesh. Okay.
If there is a space, please remove it. Yes, anyone else? Okay, actually the simulation is over, so we will view the results, so it will be convenient. To view the results, there is one last command which we have to do, which is reconstruct par, which is already mentioned in the PPT. So you just have to reconstruct everything because we just decomposed everything into 8 different parts. Now we have to reconstruct everything into a single simulation file. So I will run reconstruct par, and that will start to merge everything into proper simulation files, which we would have got if we had run in a single core process. Okay, after the reconstruction is done, we can view the results. So what I'm going to do is just double click on the ParaView file. Okay, so if anyone has problem viewing in ParaView, so this is what you have to do. Please check carefully. Once you double click ParaView, you will not see anything here. So first what you have to do is click on this green button, apply on the left. So once you press apply, it will take some time to load this. Then you will see something like this, line alone. Then you have to press the plus Y button on the top. That will take you to Y normal plane. In this case, that is XZ plane. So by default, it will show you the pressure. But if you want to see just the mesh moving, change the pressure to solid color on the left top. Then from surface, you can change to surface with edges. Then press on the play button. So this will make you to see how the mesh is actually morphing.
I'm sorry to disturb you. I think so many members are getting the same error, sir. That is pimple foam error. Can you please check it? We actually sent the pics of that error.
If you are using OpenFOAM 9 exactly, then it shouldn't be a problem actually, because that function is there only in the OpenFOAM 9.
How to know the version of the OpenFOAM we are using? Is there any command to know?
You can take any
You
tutorial
can
case
just
and
type simple form -h
just
or something, which will just tell which version you are
yeah,
using.
just run a default tutorial case that will tell you what version you are running. For in this case, you can see that it is saying version 9. So similarly, that will show anything else other than this tutorial, because it will not show properly.
Sir, I got it.
Yeah. Okay. So I'm not sure whose window is this, the one I am presenting using
It's
3GP. Yeah, you just have to go one
It's okay.
directory back.
Yes,
You
sir.
are
Yes, sir. I
just
did it. Sir,
okay.
when doing reconstruct para, I have to go inside again.
No, you don't have to go anywhere. All the commands which we are running is on this exact directory. You don't have to change your directory at all. Everything is run in this directory.
For simple form, if I am running the system, it is not running.
No, just check if you are on this right directory. Only then you will see the results.
Can you show the command
Harish?
again? Reconstruct para.
Yes. So the reconstruct par will be this. You can also find that in the PPT. Yes,
Okay.
Nikita.
Can you please repeat why we use the extrude?
Okay, OpenFOAM uses the method called finite volume method, and it cannot understand 2D mesh. Okay, so 2D mesh is something which is beyond OpenFOAM's capability. But block mesh, the mesh which we are using or which we are creating using block mesh command, is a 2D mesh. So when we type extrude mesh, all the mesh here, which you can see here, right? Everything here. So all these will be extruded to some extent. You can see some thickness. So to create this thickness, we are typing extrude mesh. Else it will just be a 2D mesh, which OpenFOAM cannot understand. So when we type extrude mesh, that 2D mesh will be extruded into a 3D so that OpenFOAM can solve.
Yeah, thank you.
So if you want to check your mesh morphing, you can press on the play button, and for each time step, you can see how the mesh actually moves. Okay.
Hi Harish. During the previous lecture, Chandan was saying about two types of mesh morphing. One was exponential and one was the other one. I don't remember the name. Which one is this?
What is the other one actually? I think he said about overset and the mesh morphing. This type of mesh morphing is known as the just a second. It is called interpolating body.
Okay.
So you can find here. So it is called interpolating solid body motion solver. So we are using that type here.
Okay. All right. Okay. Thank you.
Okay. To view the velocity, how velocity changes, you can again change to surface, and instead of solid color, you can choose velocity. Your colors might be different because of different para view. And also you can play here to see how the velocity plot changes. You can actually see the mesh is moving. That's it about the simulation part. If you want to save this as animation, you can go to File, Save Animation, give any name, probably animation, choose MP4 format, click OK, and you can change the frame rate. 10 would be ideal, 10 or 15 would be ideal. Then you can press OK to save animation. So you will get that as a video. Okay, one last thing which we will be doing is plotting the graph of coefficient of drag and lift. If you can remember, we added a function to calculate force coefficients, which is present in this folder called the post processing. Inside that, we will be having 3 folders for force coefficients, residuals, and y plus. The one which we are interested in right now is the force coefficients. It will be a .data file, .dat file. When you open this, it will have something like this. 6 columns. So the first column is time step, the second column is coefficient of moment, then coefficient of drag, then lift coefficient, then there are other two components of the lift coefficients. So to plot this, you can either use Excel or Sheets or Python, but there is a utility in the OpenFOAM itself, which is foam monitor. To plot this on a logarithmic graph, you should mention foam monitor space -L. Then we are going to navigate it. So the folder is post-processing folder. Inside that we have force coefficients. Inside that we have 0, and inside that we have the force coefficients.dat. So after I type this, I can give enter, and we will get a GNU plot which will look something like this. So sometimes it crashes based on the system. So that is the force coefficient file which we are getting.
Sir, is this code will not work in OpenFOAM 7?
I'm not sure if the dynamic mesh deck will open. So it has interpolating solid body, which is works only in OpenFOAM 9. When I tried, it did not work in OpenCFD version. So you can try it. If it doesn't work, it will show you what kind of models which you can use on the command prompt itself. So you can try replacing, read the documentation, then you can explain it.
How much are that is how to update it? Is there any tutorials in the online like that? We can we update that OpenFOAM 7 to 9?
Hello.
Yes, sir.
Yeah, one minute. So the installation instructions that we have given to you, those are for OpenFOAM v9. So if you follow that, you should be able to install it. So we were very selective in telling you why to use OpenFOAM v9, because as Harish pointed it out, right, that when we move from one version to the other, there are certain changes. OpenFOAM will always try to simplify things, change things. So there's some files which are working in the previous one may not work. Some functionality will change. Some functionalities will be clubbed. So based on that, what works in OpenFOAM 7 may not work in 9. And if you're using, say, version higher than 9, then also it will be difficult. So that's why, we were very specific in mentioning that you install only OpenFOAM v9. So that whatever case files that we give to you will work without any problem. So for people who have installed some other version, we request you, please install OpenFOAM v9 so that you will be able to follow without any problem. So if you do this today, because in later on again, the same problem will keep coming to you in other sessions as well. So please install v9. The instruction sheet has already been given to you in the email. So that the instruction sheet that was given was for OpenFOAM version 9.
Okay, if that is all, we are running out of time, so we can wrap up the session.
So thanks a lot, Harish.
Yes.
I hope all the participants have understood and will actually continue to practice the commands and execute everything that you just learned. Yeah, yes, who is this? Parth?
It's part, yeah. When I'm doing the foam monitor, post-processing, force coefficient, I'm just getting a flat graph.
Okay, did you type the force coefficient foam monitor space -L?
Yeah, I copied the same from the PPT and I'm getting a flat graph.
So did the simulation run till the end?
Yeah, the simulation ran. I was able to see everything in Parafoam. I even got the video and everything.
Then you try plotting some other software like Excel or Python or Google Sheets, because sometimes GNU plot will scale up everything. You can actually zoom using a scroll button.
Okay,
Use
so
control.
is there a way to all right, okay, so if I go in there and copy the .dat file and open in Excel,
you
it is working.
You can copy the .dat file, import it in any plotting software, then you can plot it.
Thank you. Bye bye, everybody.